Today we'll be talking about philosophy of science. Why is philosophy of science important in a research methods class? To a great extent, we're talking about worldviews, and our ability to understand the world truthfully, accurately, and so forth depends to a great extent on our understanding of the way the world is. And when we ask how the world is or what reality is, we're dealing with philosophy, not observation and not research. And so it's very important to understand as Christians what the impact of worldview may have on us. In the field of philosophy of science, there have been three main positions on, quote, what science is. First was positivism. According to this position, the goal is to develop unchallengeable propositions about the world based on logic and empirical observation, that is, using your senses. Therefore, we should stick to those things we can observe and measure directly. This position, therefore, precludes supernatural phenomena, the world of the spirit and the soul, and so forth. So the positivist view was the main scientific philosophical view through the 17th through the 20th century. And to a great extent, for mainstream scientists, there tend to still be a strong positivistic current in terms of how they view science. The goal then was objectivity, the ability to see the world as it really is, free from bias. The problem, however, was that others showed how this position in itself did not adhere to positivism. In other words, the assertion that the best way to understand the world is through observation and logic itself can't be proved by logic and observation. And so therefore, in and of itself, the position requires faith and subjectivity. And so therefore, a second group suggested what's now referred to as post-positivism, and advocates included Karl Popper, who suggested that we can't come to knowledge that is irrefutable based on observation. Instead, knowledge is always speculative, but the scientific method can provide relatively solid grounds for that speculation. They suggested that the positivists' goals were unrealistic and possibly even unscientific because of that reliance on a faith statement, that the only way to know is through observation and logic. So instead, the goal of the post-positivists was much more humble, I guess, would be a good way of saying it. And so instead of striving for objectivity, they strove for what's called intersubjectivity, which is simply an agreement about the reality from comparing results. So rather than trusting that our senses are completely unbiased, you rely instead on the collective wisdom of a number of observers who all, we hope, triangulate then on the truth from all of these various scientists doing research. And so the idea is that we triangulate on what's true, rather than relying simply and to some extent via a faith statement on observation and logic alone. The third position, postmodernism, which often is attributed to Thomas Kuhn, who was a historian and sociologist of science, is an even more radical position. The postmodernist, or sometimes referred to as the radical view, suggests that, in fact, objectivity is probably impossible in science. That instead, how we understand the world is dictated by what are called paradigms, or sometimes known as worldviews. And therefore, those paradigms dictate what scientists focus on. It's the lens through which everything is interpreted. And so therefore, knowledge is socially constructed based on a paradigm rather than discovered, which is the position of the positivists and the post-positivists. And so the postmodernist view suggests that there's even less or even more ambiguity in our understanding of reality through the scientific process. So these are the three main philosophical positions on what science is. And so you should note the difference in what their underlying assumptions are about the world and about our ability to accurately understand it and capture what's going on. Now we take a step back and look at, in general, for the scientific process to work, for the scientific method to work, there are certain assumptions that are required in order for us to conduct science. And what you should note is that these assumptions themselves cannot be demonstrated by the scientific method. Instead, they are what you might call faith statements that are required to be true in order for the scientific method to work. So that if any one of these assumptions isn't true, and especially we're talking about the first four, then in fact, science can't be done. So in other words, there is no way that you can develop a research study or an experiment that demonstrates that, for instance, the universe is orderly. Instead, that is the requirement and the assumption that has to be believed about the universe in order for the scientific method to even work. And so as you look through these four assumptions, I want to emphasize once again that these are required assumptions, or you might call them belief statements or a creed, in order for us to trust the scientific method. So that, for instance, when an experiment doesn't work, or when some research study doesn't support a theory, we don't automatically question that, oh, I guess the universe is random, or I guess things don't affect each other, or I guess the way nature works today changed from the way it worked yesterday, or it must be fairies or goblins who are affecting my results, which would be a repudiation of the first four assumptions, for instance. Instead of questioning these assumptions, instead we try to find another reason why our research study failed. But we never question that the universe is orderly and that there are logical processes that happen, or that these processes follow laws and rules. We never question the fact that there's a causal relationship, that if A happens, then it will affect B, if there's a causal relationship between those two. We also never question the fact that nature is uniform. In other words, that the law of gravity is the same 1,000 years ago as it is today, and the law of gravity will continue to operate in the same way 1,000 years from now. And that the law of gravity works here on Earth the same as it does on Venus or on Pluto or in the Crab Nebula. And then finally, and this is where there's a lot of contention, of course, when we talk about conflicts between, quote, science and religion, or science and faith, unquote, that the only causes that are worth studying are natural causes. Now, I want to point out that saying that the only causes that we can investigate are natural causes is different than saying the only causes that exist are natural. And as my bullet point shows, what you have there is confusion between the boundaries of science, that science can only study that which is a natural cause. That doesn't mean that supernatural causes don't exist, but they're outside of the boundaries of science. Now that's different than a naturalistic philosophy which says natural causes are all there is in the universe, that nature is it. There is no God. There are no supernatural forces that can also exist. And so unfortunately, a lot of times scientists end up being bad philosophers, and they confuse what are the boundaries of science versus what is the reality of the universe. And so they basically make the logical misstep that if science can only study natural causes, then natural causes are all that exist. And that is a logical misstep. Now, the final assumption is not necessary to conducting science, but it makes it a lot easier. And so the final assumption is what we often refer to as the principle of parsimony, or it was known as Occam's razor because of a particular philosopher. It basically boils down to that the simplest explanation is best. And interestingly, it's simply a preferred strategy for doing science, that when we come across some phenomenon, we try to explain it as simply as possible. However, the reality in history of science is that the simplest explanation is rarely the right one. So even though we say the simplest explanation is best, that is more of an assumption or a preference for how we try to explain things with our theories than a reflection of the way the world really works. And as just one example, not really in the social sciences, but trying to explain what causes schizophrenia. So the simplest explanation for a long time was that, oh, it is a result of under or overactivity of dopamine. But very quickly we found counterexamples, and we found other factors that also seemed to impact whether a person developed schizophrenia. And so very quickly the simplest explanation fell by the wayside, because we found that, for instance, there also seemed to be a role of glutamate, and there also seemed to be a role in prenatal development that may or may not have anything to do with dopamine. And so, unfortunately, the reality of science, and the reality especially of social sciences when we're dealing with humans, is that as much as we would prefer that the simplest explanation is best, when we start to delve further and further into some type of phenomenon, we find that the simplest explanation doesn't often hold up for long. Now, as we add more variables, of course, we still have this preference for trying to explain phenomenon with as few variables as possible. And so I think Occam's razor is still a helpful guide, because if you jumped into a research project and automatically tried to investigate all of the possible factors that you think might impact schizophrenia, you probably won't learn anything. So the assumption of the simplest explanation is best is still a good operating principle for us. As we move along, I want to give some historical background to help us understand how it is we've gotten to the point we have currently, especially in terms of how much authority science is given in our culture. And so it's important to understand that there were two influences on the scientific method as it was developed in the 17th, 18th, 19th, and 20th centuries. First of all, there was a strong influence of rationalism, the reliance on reason and logic as a way of finding truth. And that came to us, first of all, through René Descartes, the French philosopher. But there was also a strong current about the same time of what we call empiricism, the importance of observation, of using your five senses as a way of understanding the world as it really is. And that came to us through British philosophers such as John Locke. The combination of rationalism and empiricism then led us to what's called the scientific method, or hypothetico-deductive approach is the more complicated term for it. And so Lord Francis Bacon is often given credit for first pulling these strands together into what we now call the scientific method. This combination of using logic and reason and observation then led to a very extreme, idealistic, and optimistic reliance on these strands to explain everything in the world, which, as I noted before, was what we call positivism. However, there was soon a reaction against this overemphasis on pure reason and unbiased observation, and that led to two different reactions. The first, and one that still falls within what we would call mainstream science, is the post-positivist approach, and Karl Popper was one of its advocates. He suggested that rather than trying to come to truth through continually using reason and logic and observation, you had to come at truth by eliminating falsehood. And so he felt that the positivists and kind of the traditional understanding of science didn't really work because you could never prove anything was true. and if you think about it, it makes sense that no matter how much evidence you get that, for instance, your boyfriend or girlfriend is an awesome person, there's always the possibility that at some point in the future, they might produce behavior that demonstrates that, in fact, they aren't a nice person and aren't awesome. And so, therefore, there's never enough evidence, so to speak, that can prove a positive statement. So instead, what Popper and other post-positivists suggested is that what we should really do is we should put to the test all of our beliefs or all of our theories in such a way that there's a possibility that we could prove them to be false, so that ultimately we end up getting a closer approximation to truth. And this relates to this idea of triangulating on the truth, that we get a closer understanding of truth by removing the false theories. And so that any theory that's truly scientific, according to Popper and the other post-positivists, is one where you can state it in a way that there could be evidence that would falsify it. And that's what's meant by falsification. And then the other reaction, which really developed in the 1960s, 70s, and forward, is what's called the contemporary or radical reaction, which basically suggested that the scientific method was hopelessly subjective, that there was no way to remove human bias, and that your paradigm irretrievably influenced how you interpreted results, how you conducted science, and so forth. And that was the position of Thomas Kuhn. And Thomas Kuhn, as we'll see in the next tutorial, had a more nuanced position than some of his followers. And so in the next tutorial on philosophy of science, we'll talk specifically in more depth about the contemporary radical postmodern view of Thomas Kuhn and contrast his position with some of his later disciples.